Unit 1.3 The Fundamental Theorem of Arithmetic.
Prime numbers. If p is a natural number with only one factor, namely then p is called a prime number. Composite numbers. If c is a natural number having at least one factor other than 1 and itself, then c is called a composite number. Note that 1 is neither a prime number nor a composite number. We are going to use factor tree with which you are all familiar. Let us take one example. Express 12,740 as the product of its prime factors. Solution. Factorize as shown here. We have factorized 12,740 as 2 into 2 into 5 into 7 into 7 into 13 as a product of primes. That is, 12,740 is equal to 2 raised to 2 into 5 into 7 raised to 2 into 13 as a product of power of primes. Theorem 1.2 Fundamental theorem of arithmetic states that every composite number can be expressed or factorized as a product of prime factors, and this factorization is unique, apart from the order in which the prime factors occur. In this method, first we have to express the given numbers as the product of their prime factors, and then find their HCF and LCM. Least common multiple. If A divides M and B divides M for natural numbers A, B and M, then we say M is a common multiple of A and B. The set of common multiples of A and B is a set of natural numbers. The least element of this set is called the least common multiple of A and B. If M is the least common multiple of A and B, then it is written as M is equal to LCM of A and B. For positive integers, the following relation is true. We accept it without proof. LCM of A and B into HCF of A and B is equal to A into B. Prove that for any value of natural number n, 4 raised to n does not end with the digit 0. Solution. If the number 4 raised to n for any n ends with digit 0, then it would be divisible by 5. Therefore, 5 divides 4 raised to n. The prime factorization of 4 raised to n would contain the prime 5. This is not possible because 4 raised to n is equal to 2 raised to 2n. So the only prime number in the factorization of 4 raised to n is 2. So the uniqueness of the fundamental theorem of arithmetic, 4 raised to n is not divisible by 5. Therefore, 4 raised to n is not divisible by 10 also. Therefore, there is no natural number n for which 4 raised to n ends with digit 0. Here are a few examples. Find HCF and LCM of 12 and 18 by fundamental theorem of arithmetic. Solution. First we write 12 and 18 as the product of their prime factors. So 12 is written as 2 into 2 into 3. That is 2 raised to 2 into 3. 18 is written as 2 into 3 into 3, that is 2 into 3 raised to 2. The common factors of 12 and 18 are 2 and 3. Therefore, HCF of 12 and 18 is 2 into 3, which is equal to 6. LCM of 12 and 18 is common factors into uncommon factors, which is equal to 2 into 3 into 2 into 3, which is equal to 36. Find HCF of 144 and 610 by Euclid's algorithm and find LCM of 144 and 610 by using A into B is equal to HCF of A and B into LCM of A and B. Solution. Here A is equal to 144 and B is equal to 610. Now, we should find HCF of 610 and 144 by Euclid's algorithm. Therefore, 610 is equal to 144 into 4 plus 34. 144 is equal to 34 into 4 plus 8. 34 is equal to 8 into 4 plus 2. 8 is equal to 2 into 4 plus 0. Therefore, HCF of 144 and 610 is equal to last non-zero divisor, which is equal to 2. Therefore, HCF of 144 and 610 is equal to 2. Now, AB is equal to HCF of A and B into LCM of A and B. Therefore, LCM of A and B is equal to AB upon HCF of A and B. Therefore, LCM of 144 and 610 is equal to 144 into 610 upon 2, which is equal to 144 into 305, which is equal to 43,920. Find HCF and LCM of 15, 21 and 35. Solution. First, we find the HCF of 15, 21 and 35. Method 1. 15 is equal to 5 into 3. 21 is equal to 7 into 3. 35 is equal to 7 into 5. Therefore, HCF of 15, 21 and 35 is equal to 7 raised to 0 into 5 raised to 0 into 3 raised to 0, which is equal to 1. Method 2. Find HCF of 15 and 21. 21 is equal to 15 into 1 plus 6. 15 is equal to 6 into 2 plus 3. 6 is equal to 3 into 2 plus 0. Therefore, HCF of 15 and 21 is 3. Now, HCF of 15, 21 and 35 is equal to HCF of 15 and 21 and 35, which is equal to HCF of 3 and 35. 35 is equal to 3 into 11 plus 2. 11 is equal to 2 into 5 plus 1. 5 is equal to 1 into 5 plus 0. Therefore, HCF of 15, 21 and 35 is equal to 1. Now, we find LCM of 15, 21 and 35. 15 is equal to 5 into 3. 21 is equal to 7 into 3. 35 is equal to 7 into 5. Therefore, LCM of 15, 21 and 35 is equal to 5 raised to 1 into 3 raised to 1 into 7 raised to 1, which is equal to 105. Note that 15 into 21 into 35 is not equal to HCF of 15, 21 and 35 into LCM of 15, 21 and 35. So the product of three numbers is not equal to the product of their HCF and LCM.